Okay, hi guys, and we are here today to continue what I left from chapter 26, and I'm going to talk about refraction of the light today. So when a wave propagates from a medium in which its speed is v1, let's say here it's moving with v1 and this is in medium 1, to another medium in which it has a different speed, for example, here in V2, in general, what happens is that if these two environments are not the same, then the wave changes its direction. Now, this phenomenon we call refraction. So let's say if I just draw a normal to the line that connects the two environment or two medium together. So this is the normal to this line. And if here I have theta 1, then the direction is changing to theta 2. So basically this is the idea behind the refraction. There is a nice example on your book that says that to see the origin of refraction, consider the behavior of a marching band as it moves from a solid section of ground into an area where the ground is muddy. So this, for example, in this figure that you see here, just imagine that is the solid ground and then the march band is moving to the muddy place. Now, in this analogy, the rows of the marching band correspond to the wavefronts of a traveling wave, and the solid and muddy section of the ground represent media in which the wave speed is different. Okay, so if the speed of the marchers on solid ground is v1, then after a time delta t, right, they have advanced a distance v1 delta t. On the other hand, if the marchers in the mud move at a reduced speed v2, they have advanced only v2 delta t in the same time. This causes the bend in the line of marchers, and you can see in this figure what happens here. Okay, if you go ahead and take a look at page 929, it gives you how the following equation that I'm gonna write for you is derived, but I'm not gonna prove it here for you because we want just to go on to other sections. But we need to know that sine theta 1 divided by v1 equals to sine theta 2 divided by v2. Okay, so this is the rule for us for the refraction. Now, sometimes it's easier just to write it as v2 sine theta 1 equals to v1 sine theta 2, right? Now, another thing that we need to define here, and that is very important in this chapter, is the index of refraction. So we show it by n, and then it is defined as v equals to c divided by n, meaning the velocity of light will decrease when it enters the medium. Okay, so if the speed of light in vacuum is 3 times 10 to the power of 8 meters per second, if it enters water or air or glass or wood or whatever, depending on the index of refraction of that medium, the velocity will change. So this is only the speed of light in vacuum. Speed of light in other mediums is different. Okay, so the n really depends on the medium. So each medium has a different index of refraction. For example, For the air, the index of refraction is almost 1, but it is not exactly 1. So light in air just moves a little less than the velocity that it has in the vacuum or in the space. Exercise 2611 says how much time does it take for light to travel 1.2 meters in water? Okay, so how much time, so I'm looking for time, does it take for light to travel 1.2 meters, right? Okay, so what I know is that the speed of light in water is gonna be c divided by n. Now, we need to find the index of refraction for water, and there is a table that you can look this number up, or if there is any problem, the index of refraction will be given to you. But for water, let's say that is 1.33. Now, I know that, just a reminder quickly here, that V equals to x divided by t, right? It's equal to distance divided by time. So I can write time is equal to d divided by v. But here, v itself is c divided by n. So let's go ahead and substitute the numbers that I have. So t equals to 1.2 meters divided by 3 times 10 to the power of 8 meters per second divided by 1.33. So one thing to notice is that the index of refraction does not have unit. Okay. Now time is equal to 5.32 times 10 to the power of negative 9 seconds. Alrighty, now that I know what is index of refraction, let's go back to the equation that I had. Sine theta 1 divided by V1 equals to sine theta 2 divided by V2. Now I go ahead and replace the velocities in terms of c, speed of light. So I can write that sine theta 1 divided by c divided by n1 equals to sine theta 2 divided by c divided by n2, and then get rid of the c here. And what I see here is this famous equation that we call Snell's law. Snell's law says that n1 sine theta 1 equals to n2 sine theta 2. All right, and then take a look at the table that you have on page 930, table 26.2, which gives you the famous index of refractions. For example, diamond has 2.42, glass has 1.66, and then quartz has 1.46, ice is 1.31, and so on. Okay, so a typical application of Snell's law is given in the following exercise. It says a beam of light in air enters A, water with index of refraction of 1.33, and B, in diamond with n equals to 2.42 at an angle of 60 degree relative to the normal. So the angle is relative to normal. Find the angle of refraction for each case. Okay, so if this is the incidence, what is the angle of refraction? Let me go ahead and just visualize the problem for you. In the first part, we have air and water, and then I just go ahead and draw the normal. Okay, so the light is entering with theta I here. So it says that the angle is relative to the normal. And then instead of just going straight, it will bend. It will bend, and because it is going through the denser medium, it will get closer to the normal. So this is something that we want to actually know, that if it is going from like less dense medium to the more dense medium, then it will get closer to the normal, to this normal line. So this is my theta r. Okay, so some of it, of course, will go ahead and reflect. Okay, so let me show this by reflect. So it is not, it's not, both of them are not theta sub r. So this theta I is 60 degree, and I know that the reflection is 60 degree because we know that the angle of incidence and reflection should be equal. But then what about theta r? So we should use a Snell's law. N1 sine theta 1 equals to N2 sine theta 2. Let's say that air is my medium 1 and water is my medium 2. So N1 is the reflexive index, the index of refraction, sorry, for air. So it is 1 sine 60 degree equals to N2 is the index of refraction for water, which is 1.33 sine theta 2. Now that is easy. I want to find theta 2. So theta 2 is sine inverse of sine 60 divided by 1.33. Okay, if we calculate this, then theta 2 will be 40.6 degree. So you see that it is less than 60 degrees. So indeed, it gets closer to the normal. Okay, so that was for part A. Part B is the same thing. So let me go ahead and just draw the same figure for you. Here we have air, and then we have diamond. So this is my environment 1, medium 2, and then the same thing, normal. So I have the light coming with 60 degree here. And because diamond is even denser than water, so I expect the beam to get even closer to the normal, right? And let's see. In this case, theta 2 will be sine inverse of sine 60 divided by 2.42. So calculate this and you will get 21 degree. So yes, indeed, it's getting closer to the normal. So let's talk about total internal reflection. Sometimes happens that refraction can trap a ray of light and prevent it from leaving a material. Now, this is strange, right? For example, now let me draw a figure here for you and let me do opposite. So I have a ray in environment 1, which is water, that goes into environment 2, that is air. Now my ray is going from a denser medium to a less dense medium. Okay, so like always, I should draw this line here. Okay, so this is the ray theta 1, and then of course, because it's entering the air, it should get away from the normal line. So it goes like this, right? Theta 2. All right, so this is the first angle. Theta 1 is a smaller angle. Now, if the same ray goes from water to air, but now with a bigger angle, so if this is theta 1, then of course it will bend more right? Now, what happens if this light, let me draw it again, from water again to air. So what happens if this beam enter the air in a way that the refraction is exactly parallel to the edge of the medium. So what happens if this happens? So here theta 2 then is 90 degree, right? Okay, so in all these cases, I have a reflection too. Here I have a I have a reflection. Here I have a reflection, and here I have a reflection too. So this should be equal. And then now, what happens if, another case, what happens if water, air, that the theta 1 becomes even bigger? So what happens if theta 1 is even bigger? So what happens that, what happens here? Now we do not have any refraction, but it will directly go back, and here we have a total internal reflection. So everything will be back into water. So there is no ray that can actually exit here in this region, right? So this is what we call total reflection. Okay, and this angle here is called the critical angle. So the angle at which theta 2 is 90 degree or sine theta is equal to 1 is called the critical angle. Let's go ahead and formulate the critical angle here. So Snell's law says n1 sine theta 1 equals to n2 sine theta 2. But then if you just go back and take a look at the figure, n1 sine, so remember that the critical angle is the one for which the refracted angle is 90 degrees. So let's call this the critical angle for which the refracted or the refraction angle is 90 degrees. So this part is 1, and I can say n1 sine theta c equals to n2 sine theta c equals to n2 divided by n1 critical angle here. Example 2615, and I'm going to only do part B. Part A is very similar, just like a different number. It says consider a sample of glass whose index of refraction is n glass 1.65. Find a critical angle for total internal reflection for light traveling from this glass to B, water. Now for water, the index of refraction is given to be 1.33. All right, now let me just go ahead and draw this picture for you. Okay, so I have two media here, glass and water. Glass is my medium 1, water is number 2. And okay, we need to remember that the total reflection happens when light goes from a more dense medium to a less dense medium. Okay, so from more less to less dense. Okay, so here I just choose a beam of light. This is my beam of light. And then I want the angle for which the refraction angle is 90 degree. This is my critical angle. right? So the question asked me find a critical angle. So what is theta C? This is my theta C. Now let's go ahead and use this equation here to solve this problem. Okay, so I know that theta C is sine inverse of n2 divided by n1. Okay, so my n1 is the glass, so this is my medium 1, and then my n2 is water, this is my medium 2, and then the critical angle is sine inverse of 1.33 divided by 1.65. And if you calculate this, the critical angle is 53.7 degree in this case. Okay, so we talked about the index of refraction and the critical angle and everything. And we saw that a ray of light can be redirected as it passes from one medium to another. A device that takes advantage of this effect and uses it to focus light and form images is a lens. Now, typically a lens is a thin piece of glass or other transparent substance that can be characterized by the effect it has on light. Okay, so I'm not going to teach everything from this section, but what is important for us is that two types of lenses that we are going to learn. So this is a concave lens, or to be more exact, double concave lens, and the other one is having this shape. This is like you know the typical opinion that people have from the lens, and this is called convex lens, to be more accurate, double convex lens. All right, so what happens is, so we need to have this principal axis like we had for the mirrors, and every lens has a focal point. So, and it has a center point. So here, let's say that this is the focal point, and here, and of course, because it's a lens, so two sides of it work. So this one, like both of them have two focal points, right? So what happens here is that in a concave lens, the beam of light enters the lens from distance in parallel. So in this one, as it is obvious from its shape, it will diverge the beams. Okay, so let me just check that they just all meet in the focal point. Okay, so this is what happens. And the other one, as it is obvious from its shape, if I have a beam of light entering the lens, so it's going from uh, like a less dense medium, for example, like air, into a more dense medium, like a glass that is for lens. So it will bend, and so here, and it will be something like this. So we do the exact same thing that we did for the mirrors, and we use the ray tracing to see the formation of image in lenses too. Let me go ahead and start with a double convex lens. Okay, so I have two focal points, one each side, and they should be exactly in the same distance away from the lens. And then you have a center point here, the center of the lens. So again, we define three rays, if you remember them. Okay, so let me place the object behind the focal point here. This is my object. Now, the P ray propagates parallel to the principal axis until it encounters the lens. So let me just draw this, and I usually do this the middle line. Okay, so this is my P ray, goes parallel, and then it is refracted to pass through the focal point on the far side of the lens, so on the other side. So if it goes parallel, it passes through the focal point. Next ray is the F ray that passes through the focal point on the near side of the lens. Near side, it means that the side that has the object. Okay, so if it passes through F here, then it leaves the lens parallel to the principal axis. Okay, so then it will goes parallel like this. So let's call this F ray. The next ray that I have is the M ray that passes through the middle of the lens with no deflection. So what passes through the middle one is called M ray, middle. Remember that for mirrors we called it C ray. So this passes with absolutely no refraction and deflection. Okay, so if I just could draw it more neatly, you would see that all of them are meeting here in this point. So your image is inverted and it has the same length as the object. This is your image. So you see that the magnification is 1. Okay, so in this case, the image is real. This is something different from the mirrors, right? Because in the mirror, if the image was on the other side of the mirror, then it would be virtual. But in lens, actually, because you expect the image to be formed in the other side of the lens, because now you have two sides. Lens is just a glass. It doesn't have any side that is blocking the light. So because it is where it should be, which is actually on the other side of the lens, then the image is real, and of course it is inverted. Okay, so next, let's just consider the concave lens. Okay, so and then I'm going to give you exactly the same rays that we use for the other lens. Okay, so let me just place the object behind the near focal point. This is my object, and again, the first ray that I'm going to talk about is the P ray. P ray. Okay, we know that in this type of ray, the beam of light needs to diverge. Okay, so same as what we did for the mirror, it goes away from the principal axis in a way that its tail or its continuum passes through the focal point. So this is my P ray. Next one is the ray that passes through the middle, and that passes without any type of refraction or deflection. So if it passes this way, then it just continues this way, and this is my M ray. The third one is the tricky one. So I'm looking for the F ray, right? F ray should have something with a focal point. So we'll go ahead and say that if I have a beam of light that passes through the lens in a way that it would pass through the focal point if it were not to refract. So if I had a ray that would pass through this focal point without being refracted, but we know that it will refract, of course, then it will refract in a parallel to the principal axis. Now this is the F ray, okay? So because I know that the beam of light cannot just like go in a straight line unless it is passing through the middle point, and this is the only place that the ray is passing without refraction. So if I had a beam of light that would pass through the focal point, the far focal point, like to the other side of the lens, if this was the direction of the ray, then it goes parallel to the principal axis. Okay, now this is a tricky one, and to learn more, you can take a look at figure 26.45 in your book. So anyway, we have these three rays. Now they are diverging, right? They're just like getting farther and farther from each other. So how is the image then formed? So like what we did in the mirrors, I need to continue the rays until they hit each other, right? So it's a little clean, not clean, but anyway, because I do not have the colors here, it might be difficult for you to just see what happens here. But if you take a look at your book, it gives you a better idea. So this will be my image. Okay, so this is a smaller, and because it is where it is not supposed to be, because it's in the same side of similar to the object, then it is virtual. So here the image is, so in that sense, lenses are working opposite of the mirrors. So if the image and object are in the same side, then the image is virtual and it is upright. And it is smaller. Okay, so like always, we need a formula or an equation to describe how the image is formed. Now, the most famous equation that we use for lenses is a thin lens equation, and I say thin lens because that is only applicable if your lenses are thin, meaning that you don't have like a thick medium. As for the lens, there is no thick glass there. So if this is the case, then I can just write 1 over dO plus 1 over di equals to 1 over f. And this is very similar to what you had um, to the mirror equation. So dO is the distance between the object and the lens, right? So this is object distance to the lens. Di is the image distance, and f, small f, is the focal length. All right. As for the magnification, so again, similar, m equals to negative di divided by dO. Okay, So rules are a little different from the mirrors, right? Because here we are working with the lenses, but I will kind of organize them here for you. For the focal length, f, so f is positive if you have converging lens or convex lens. So convex lens, because it converges the rays, so this is converging lens, then focal point is positive, and it is negative for the concave lens or for diverging lenses. Okay, magnification. Magnification. Okay, magnification is positive if the image is upright, and it is negative if the image is inverted. Image distance, or DI. So DI is going to be positive for real images, and just pay attention that here real image is the image that is on the opposite side of the lens from the object. So opposite side of the lens from the object. Okay, and then DI is negative for virtual images. Now, virtual images are the one that are on the same side of the lens as the object, on the same side of the lens as the object. Last one is the object distance, or DO. This is positive for real objects. Real objects, it means from which light diverges, and of course it is negative for the virtual objects. So this is for the virtual object, which means toward which light converges. Now, we are not going to talk about virtual objects here in this chapter, but there are examples of virtual objects in chapter 27. Unfortunately, I have to skip most of chapter 7. Of course, I recommend that you go ahead and study chapter 27, because it has a lot of good information about telescopes, microscopes, how our eyes work, but due to the lack of the time, and because we had like one extra week for spring break, I have to like make this course a little more compact than what I originally planned for. But please go ahead and study yourself. There won't be any question from chapter 27, but feel free to email me or inbox me if you have any question. The last thing that I'm going to do for you is to solve example 2618 on this chapter. This example says a lens produces a real image that is twice as large as the object inverted. So I'm going to write down the description of the image. It is real, it is inverted, and it is located 15 centimeters from the lens. So I know the eye is 15 centimeters. And it is twice as large as the object. Okay, so I know that magnification is -2. Find the object distance, what is DO, and the focal length of the lens. Okay, because it says that the image is real, then I know that my lens should be a convex lens. And then because the image is inverted, so magnification is negative. So this is how I get the negative sign here. And because it says the image is double, twice as large as the object, so it means that magnification is negative 2. Okay, so in part A, when it asks for DO, I am using the equation for magnification. Magnification is equal to negative DI to DO, and this is given to be negative 2. So this means that DO is DI divided by M, and I just got rid of the negative signs here. Okay, so if I replace for this, DI is 15 centimeters divided by 2 without the sign, because I have already counted the sign is negative 2 in the negative 2. So this is going to be 7.5 centimeters. So this is the distance between my object and the lens. Okay, part B asks for the focal length. I use the thin lens equation, 1 over f equals to 1 over do plus 1 over di. Because my image is real, so di is positive. Because it is a convex lens, the focal point is positive, and my object is of course positive, so I just replace the numbers here. 1 over f equals to 1 over 7.5 centimeters plus 1 over 15 centimeters. So this is going to be 1 over 5 centimeters, and then f is 1 divided by 5 centimeters inverted, which is 5 centimeters itself. Now, if you have noticed, I'm not converting the units. I just keep it as the centimeters because, I mean, in this kind of equation, everything is in the unit of centimeters. So if these two are in the same unit, then F will be in centimeters. So as long as you keep the units the same, you do not need to convert the units. Okay, so this brings us to the end of this chapter. And then there is like a small section about dispersion and rainbow. I let you study that yourself. We have covered everything that you need to know from this chapter, and I hope that you enjoyed the lecture.